Hopefully everyone can hear you now, Hannah. Just let us know here in the chat.
Okay. All right, so I'll recap what I said there. The short version, apologies for the delay. That was my fault for messing up the daylight savings time shift. But here we are. We're at Unit 7. This is, again, this session here is based on the assumption that you already have some familiarity with the content in Unit 7. And as always, please ask lots and lots of questions, drop them in the chat. I'll pause periodically for questions, and Mike will let me know what you all are asking. Today, what we are covering, well, the Unit 7 topics, right, are what's in a transaction, specifically looking at fees, the transaction timeline, so what happens, as the transaction is created and broadcast and goes through the mining process, etc. And then the really big topic for this unit is scripting. And that's what we're focusing on today, is learning a bit about Bitcoin scripting. So I'll pause here just to make sure, Mike, everyone can hear me. Am I getting some people that can definitely hear me?
We're good to go.
Okay, cool. All right, so scripting, and if you're, a developer and you're used to building things in PHP or Python or JavaScript or Golang or something like this, Bitcoin scripting is going to look really foreign and really weird. It's basically kind of a very old school sort of simplistic way of doing things, right? It's not like a modern programming language. So it can be a bit difficult to follow along with what's happening. When you see a script, it's kind of written backwards, and we'll walk through it, and we'll look at lots of different examples, and then we're going to go use a Bitcoin script simulator and walk through different examples to try and just get a feel, try and get a picture in our head of what's happening here and how Bitcoin does things, right? And then we'll touch a little bit on some advancements right at the end. We'll just walk through a couple advancements in Bitcoin scripting. But for the focus for today is really to hopefully give all of you just a good picture in your head of how Bitcoin handles what this Bitcoin script looks like and how Bitcoin processes it. Cool. So let's get started. First, though, we're going to go over some notes on a couple of other parts of this particular unit before we really dive deep right into the scripting. So we're going to talk about fees. Now, last week, if I remember correctly, last week is when we went and set up a little reg test node, and when we actually created a transaction and then signed it and broadcast it and went through all of that. And so there we got to look at fees and how they're input into a transaction and how they work, right? So first on that, if you remember what we did is that fees aren't directly specified in a transaction. Fees are what's left over, right, between the inputs and the outputs, right? So you have a certain amount of inputs and that goes into a certain amount of outputs, and then you should include a fee, right? And in that difference, there's going to be some small difference between that, and that's the fee. And again, of course, remember, we try and put absolutely as little data as we need to on the blockchain. So because just having the inputs and outputs gives someone else enough information to calculate what the fee is, we don't need to clearly, separately specify it because there's enough information there to recreate it. So we never put more information than we need to in a blockchain, right? Because space in a public blockchain is scarce and expensive, right? So we don't do that. All right, so a few other notes here on fees. All right, fees serve as a security mechanism themselves by making it economically infeasible for attackers to flood the network with transactions. So let's think about that for a minute. It's kind of like a spam prevention mechanism, right? So one potential attack on the Bitcoin network is to just flood it with fees, right? Just absolutely fill up all of the blocks with these just frivolous, or depending on your point of view, right, just frivolous transactions for small amounts, right? Just fill up the blocks, flood the network with that data. It's like a DDoS attack, right, on the blockchain. And you could do this now, but what would happen because of fees is it would be incredibly expensive for you to do that. And as you attacked the network, the fees would rise and rise and rise, making it more and more and more expensive for you to do that, right? So in this way, it serves, fees serve to protect and secure the network. All right. They are an incentive to include or mine a transaction into the next block, right? So they're a way to signal, right? Sort of space in a block is like, this market space, right? And if you have a transaction that's really, really important to you and has to go through right now, you can include a really high fee, right? To entice a miner to, and it's the software doing it, right? But their software will look at it and say, oh, that transaction must be really important. It's got a really big fee. I like fees, right? I'm programmed to get as much fees as I can from this mining process. So that one's definitely going into the next block, right? Well, in contrast, if you have a transaction that doesn't matter if it goes through now or next week, whenever you just want to get it on its way and not think about it, and then you can set a really low fee. And at some point when the block space, the mempool is way down, that transaction room, waiting room is kind of empty, then that transaction might get thrown in there and included in the block, right? So it serves that sort of signaling mechanism. All right, as we discussed, fees are implied as the difference between the sum of inputs and the sum of outputs. And transaction fees are calculated based on the size of the transaction in kilobytes and not the value of the transaction in Bitcoin. This is interesting, right? And this is an interesting characteristic of how Bitcoin operates and Bitcoin does things. I think we're very used to thinking about fees in terms of sending money as a percentage, right? If you wire money or if you're using MoneyGram or something like this, generally that fee is some sort of percentage of what you're sending. But for Bitcoin on the main chain, not like the Lightning Network, that's a bit different, but on the main chain, fees are based entirely off of how complicated that transaction is, right? Which makes perfect sense, right? Because again, this is another sort of attack vector where I could just create really, really complicated transactions that everyone on the network has to validate. So it's going to consume the computing power of everyone on the network. And I could do that by just sending out lots of really, really complicated but low value transactions. And if the fee were based on the units of Bitcoin being sent, this number of Satoshis, well, that fee would be low, even though we're consuming a lot of resources on the network, right? So instead, fees are based off the size of the transaction. And so if there's a really, really big, complicated script that's going into this transaction, which we'll talk about shortly, then, with lots of signatures that have to be validated and all this sort of stuff, then you would expect that you would pay a much higher fee for that transaction, right? So I could send a super complicated transaction that's only sending $50 worth of Bitcoin, and I'm going to pay a much higher fee than if I send a very, very simple pay to public key hash like transaction that sends, $1 million of Bitcoin. Right? The fee on that $1 million transaction is going to lower a very complex $50 transaction. And that serves the purpose to prevent misuse of the computing power on the network, right? But it's very interesting, and sometimes that's, counterintuitive to how we're used to thinking about fees on payment networks. So before we go into before we dive into scripting, I will pause here and see if anyone has any questions on fees. So there's still some lingering question that you have about how this works. Now is a great time to type that into the chat. And Mike, let me know if we have any questions there. How are we doing, Mike?
All right, we're doing okay right here. I'll give everyone a chance to put their questions down there
Is he
in the
perhaps
chat.
muted?
Check anything. I will say, we lost your internet there for a second. Did you switch your internet over?
Maybe he's gone to get a cup of coffee. Okay, so we'll carry
sorry
on.
I'm sorry. They heard me. You didn't hear me. Sorry about that,
everyone. Gotcha. Okay.
Yeah, now everyone should be hearing both of us. Sorry about that, everyone. Yeah, no. So we're not seeing any questions yet here in the chat, from what I can see. So I think we'll go on at this point, and I'll do the other thing I mentioned on the back end. Don't worry.
Okay, cool. All right, so we're going to move on to scripting, and I'm going to try to go through this very slowly, and it's probably going to be a lot of repetition of ideas. But again, like so many things with Bitcoin, is that it's often very new, sort of a concept, so it's hard to relate it to something if you're not, if you haven't studied like old school computer programming, then this is going to be sort of new stuff and kind of confusing and hard to read. And so we're really going to go through it slowly, and we might get kind of repetitive, but hopefully that really helps embed, the structure of what's happening here. All right, so notes on Bitcoin script. All right, it is a Forth-like reverse Polish notation stack-based execution language. All right, and when I first read that, learning about Bitcoin, that made absolutely no sense to me. And the first time you read it, right, unless you studied, old school programming, probably isn't going to make much sense to you either, right? But maybe that's stack-based, right? Some of the, computer science students, right, will understand what that's talking about. But basically it's saying, hey, this is kind of an old school way of doing it. We're using like reverse notation. So things are kind of written in like the opposite order from how like a human is used to reading it. And it's stack based. So we have the stack, information and, instructions pile up on the stack and then, get taken off the stack. And we'll talk a bit about that. So, this is technically what Bitcoin script is. It's something a little bit different. We'll walk through it step by step. All right. It's a very simple language that was designed to be limited in scope and executable on a range of hardware, right? So the simplicity is a deliberate security feature, right? So there's a lot of people that wanted to build really complex things on Bitcoin and found they could not, because the Bitcoin script just doesn't allow for that level of complexity. This is, to go do some Bitcoin crypto history, this is actually how Ethereum started, is, Vitalik and some others were trying to build some complicated functionality on Bitcoin and realize that, hey, it's just, you can't quite make this thing do what we want it to do. It's not flexible enough, right? It's very rigid and limited. And so they went off and created Ethereum, right? Which does have all the bells and whistles and is this really complicated, has, sort of more, much more complex functionality than Bitcoin does, right? And some people, and I really don't think people like to do the Bitcoin versus Ethereum, and to me, they're apples and oranges, right? They're two different systems chasing different goals. So for Bitcoin, you can think of it as a drawback that it doesn't have a lot of this functionality, or you can think of it as a feature, right? Because it's so simple in what it's doing, it's much harder to sort of manipulate or abuse or have things go wrong in Bitcoin because, there's no loops. It's not Turing complete. Like it's very simple. So with, Ethereum, how Ethereum processes things, and the smart contracts that go on there, you can see all sorts of crazy bugs and weird hacks that happened on different smart contracts and stuff. And that's enabled because it's so much more complex, right? So this isn't necessarily a drawback. This is just like different design choices chasing different goals, right? But Bitcoin, no doubt, is very simple and thus limited in many ways. All right, Turing incompleteness. So there are no loops or complex flow control capabilities other than conditional flow control. So that's all very computer sciencey. We can sum that up and say, you're not going to do loops in Bitcoin, right? Any Bitcoin scripting is going to happen. There's not going to be loops, right? So if you're and if you get to the point where you're building, scripts or, Bitcoin does have, what you might call a smart contract. Like you can build all kinds of programs on top of Bitcoin and using Bitcoin scripts, but you have to build it, very differently than you would build something, say in Python, right? It's not blockchain based. So it's important to keep in mind the very specific rails that this stuff runs on. All right. This prevents infinite loop or other form of logic bomb that could be used as a denial of service attack against the Bitcoin network, right? So, if you had, right, like if you enabled loops in Bitcoin scripting, Bitcoin transactions, then one potential thing that could happen is that someone could just write an infinite loop into a transaction and sort of all of the computers, all of the nodes on the network that are trying to validate that transaction could just get stuck in that infinite loop. Now, there are of things you can do about that. Ethereum deals with this by, their gas fees, right? You can only expend so much computing power while, processing a transaction. So there are other methods of dealing with this. But what Bitcoin has done, because it's got a very simple goal that it's chasing, right? It's not trying to be the Swiss Army knife of crypto. It's trying to be Bitcoin, right? So it just, loops aren't allowed, right? And so we don't have that problem. All right, stateless. So all of the information needed to execute a script is contained within the script. So basically not having to keep a track of all of the different states of different things. It's just keep a track of the blockchain, right? And you're good. All right, before we get into locking and unlocking, that's a lot of information there. Mike, do we have any questions at this point?
All right. You can hear me right now. We'll just check it first.
I can hear you now. We're all good.
I'm not seeing any questions yet down in the chat. Someone says it's basically a programming language with the looping stuff. With stuff like looping missing, which isn't really a question, more of a statement. But
yeah, I mean that's basically correct. It's like a very simple. That's why they sort of call it scripting. It's very, very simple. But yes, when you go to write it, you get a very specific and much smaller than you might normally have, like, set of kind of functions that you can use, and you can't do loops, right? So you can think of it as just a very, very simplistic programming language. Yeah, that would be a helpful way to think about it, probably. Yeah.
All right, awesome. Well, I'm not seeing anything else down there, but again, of course, if anyone has questions at any time, feel free to put them down in the chat, and I'll let you know.
Awesome. All right, let's move along to the locking and the unlocking, which we have been through many, many times now, but it is just as relevant as it was the first time we talked about it. So, all right, a locking script is a spending condition placed on an output. It specifies the conditions that must be met to spend the output in the future, right? So we know that. We've talked about UTXOs. You have inputs to a transaction, and then what comes out of that is the outputs, which are locked with a specific locking script. Those are our UTXOs, unspent transaction outputs. They exist there. In the future, perhaps we can unlock them and send them on somewhere else, right? They're potential to be spent. They have the potential to be unlocked. All right. An unlocking script is a script that solves or satisfies the conditions placed on an output by a locking script and allows the output to be spent. Cool. So we lock it with a certain criteria, and then an unlocking script satisfies that criteria. Basically, we put a bunch of stuff on the stack. We put more stuff on the stack, right? We process it. If the final result comes out to true, it's like, aha, unlocked. Spend your Bitcoin can go on its way to its next home, right? Go get locked somewhere else. All right, so let's look at this, and again, we will come back to this in some depth, right? So we're going to keep sort of cycling through this example. All right, so here we have a very standard pay to pub key hash transaction, right? This is our locking script. This is what it looks like. This is dupe hash 160. Here's the hash of a public key. This is equal verify, and this is check sig. Okay, and these are our opcodes, and we'll look through them in a minute. In all the Bitcoin opcodes generally start with OP underscore DUP, right, for op dupe, right? But this image is taken from the Mastering Bitcoin book, and what happens in that book is because op is at the front of all the opcodes, it's redundant, so it's kind of just removed for simplicity. But we'll go and look in a minute at some of the available opcodes in Bitcoin scripting. Okay, so here we have, this is the locking script. He says, hey, duplicate hash. Here's another hash of a pub key. We're going to check that they're equal with a verify. That's the book, the Unit 7 covers sort of what this verify is. Some of these opcodes have this verify on there, just kind of additional step. We'll leave that for the book. Right now, we just want to get the flow of what's happening here down, and check sig, okay? So this is what a locking script looks like. This is what the unlocking script looks like. Here's a signature, here's a pub key. That unlocks this. At the moment, if you haven't read through this chapter of Mastering Bitcoin 3 times already, you might be looking at this going, but like, how does that unlock that? What's happening there, right? And so we'll walk through it step by step. Okay. Apologies, because I sort of ran out of really nice pictures to use for this unit of the course. Normally I like to have lots of nice pictures, but for this unit, I resorted to using some Wikimedia Commons images. I made a note for myself to, have my graphic designer create a nice image to try and explain this concept. So this is a stack of plates, right? We all probably have this sitting in a cabinet in our kitchen, right? But I show you this because it can be helpful to visualize this while you're thinking of what's happening in a Bitcoin script. So we have some data, right? And we'll walk through what goes on the stack. But you can see you have some data and it's like a plate and you put it down. Then you have some more data and you put the plate on top of that. And then you have some more and you put that plate on top of there. And it can stack up to this sort of pile of dishes, right? And we talk about there's a really, in the course, there's a really excellent video of Andreas walking through sort of a scripting workshop, right? Where he talks about push and pop and walks through a pay-to script hash transaction. It's really an excellent resource for understanding this stuff. And then you talk about push and pop, right? So you push data onto the stack and you pop data off of the stack, right? And this happens in the last in, first out, right? Basically means you always have to take from the top of the pile, right? If you have this giant stack of plates and I try and pull a plate out from the middle, the whole thing might crash and break, right? So you're always going to take like the plates on the top, right? You start on the top, work your way down. It goes up and down, sort of like that throughout the scripting transaction, validation process when that script gets processed and run. Okay, so any questions on this image? We'll walk through it, and we're going to there's this great website that lets you try out different scripts and sort of visualizes it for you going on the stack and pushing data on the stack and popping data off the stack. It's really, really helpful for the visualization of it. So we'll walk through that. Mike, jump in and let me know if there's any questions here. Yeah.
Well, I can first jump in and say, I think I have that exact stack of plates in my
Nice.
But I'm not seeing any questions coming up in the chat right now. But of course, as always, if you do have questions, you can leave them there in the chat. And if you're watching later, you can leave them in the comment section below.
Okay, awesome. Okay, so let's move along, and we are going to go look at this, which is, I think, this one. Yes. Okay. So what we are looking at here is a list of, here we go, Bitcoin opcodes. And this is the exact same thing, right? Bitcoin uses a scripting system for transactions. A fourth light script is simple, stack-based process from left to right? So the same, and this is, a good resource too. You can read through this. It's going to, we're covering what's in here is basically what we're covering now, but a little bit more technical details that we're not really going to dive into today, vector bytes and, how many bytes long, etc., blah, blah, blah. So lots of technical details, if you really want to dig into that. But what we want to do here is just get a brief idea of what type of opcodes are out there and what they do. So let's see if I can, here we go. Op-dupe, this is one that we're going to look at today. Duplicates the top stack item. So sort of pops off whatever's on the top of the stack, duplicates it, and pushes it on two of those, right? Now there's two of them. So that's what it does there. What else can we look at? Oh, splice, interesting. There's a decent amount of options here that you can use for all kinds of different scripting. But let's look at op equal verify. Same as op equal, but runs op verify afterwards, right? Op equal returns 1 if the inputs are exactly equal, otherwise 0. Okay, so it's like, are these two things equal? And op verify, where's op verify? Maybe we'll look at that. Come on, op verify. Okay. Marks a transaction as invalid if the top stack value is not true. The top stack value is removed. Okay, so I think this is just with verify at the end. It's just like, if you fail, we're just stopping processing. Like, we're done. All right. So we could go through and, dig through all of these. And if you really get into, working on something that requires Bitcoin scripting, then you'd really want to be aware of this resource. There's a whole list of opcodes out there. You can come here and dig through what each of these does. Some of them are very simple, like op add. Hey, you add two things together. Op sub, you subtract one thing from another, etc. And then some of them can get really complicated, right? So here's check sig, which we'll be using a lot, which, hey, check the signature. But here's check multisig, which we won't dive into today, but hey, that gets, we'll talk briefly about multisig, but hey, that can get kind of complicated, right? So there's all sorts of different options you can use, all sorts of different opcodes, which you can think of is just like a function you would run, right? Like if you were writing something in Python, Python would come with like a certain set of functions built into it, and you could just use those functions. And so you can think of Bitcoin scripting kind of like that. These are the sets of functions that you get to work with. Cool. All right, so let us come back over here and let's walk through.
Hey, Hannah, we have a question real quick.
Yep.
If now's a good time.
Now's a great time. Let's do it.
Alrighty. Question here. Said sorry if they missed it, but all the data the script operates on is included in the script itself. So the question is all
right.
It's all yeah. You got it.
Yeah, so there's not, so all the data that it's going to operate with is included in that locking script, or is maybe like referencing something in, the previous transaction, right? So you can go and look at the previous transaction where that output came from, right? And sort of look there, right? So it might reference out to like the last transaction that output came from. But basically, like if it needs to, validate a signature, as a pub key or something, it's generally correct to think that all the information you need is contained in that locking script. So you need the locking script, and you need the unlocking script. It's possible you might want to reference something in a previous transaction. Yeah.
Okay, awesome. Well, let us know if that answered your question, and I'll let you keep going, and I'll let you know if there are any other questions.
Okay, cool. All right, I tried to make this a decent size, so hopefully it's not too small of a font for us to read here. You might want to put your YouTube on full screen for this one. But here, let's walk through a pretty simple script, right, that we're just going to process, right? Just for a simple example. Okay, so we have, this is our script, 2, 3, add, 5, equal, right? So again, this would actually be op add and op equal, and we could go back to that website that lists the opcodes and look up exactly which one's doing if you're ever reading a script and you're not sure how to process, how to understand what's going on there. All right. Now, because I've read through this stuff many times, I can look at this and read this and go, okay, right, that's simple. It's taking 2 and 3 and adding it and checking that it equals 5, right? But it's kind of written backwards and it's confusing. So let's walk through it slowly and look at what's happening on the stack. We have our execution pointer, right? Take this number 2, boom, we push that onto the stack, right? Okay. We then move along, the execution pointer goes to 3, boom, and we push that onto the stack. Now, if we go and look at op add, I believe it pops 2 parameters right off the stack. So let's just go and look at that. Oops, not this one. We'll come back to that in a minute. But if I just do, op input, right? So it pops 2 parameters off the stack and pushes 1 on, right? That's what we would expect. Think I'm reading that correctly? Okay, so now we get down here to the op add, right? So we're here, we have 2 parameters or 2 bits of information on the stack. Then we get to this op add. Op add pops the top 2 items out of the stack and adds them together. Then operator add pushes the result 5 to the top of the stack. So it just takes those 2 numbers, right? Pops them off the stack, adds them together, takes that result, which it gets, which is 5, and pushes that back onto the stack. So now this is what our stack looks like. It's just 5. Now our execution pointer moves along to the number 5. That's just some data, so it gets pushed onto the stack. So now we have 5 and 5. Then we get to equal, right? What does equal do, right? Operator equal pops the top 2 items out of the stack, compares the value, 5 and 5. And if they are equal, equal pushes true, true equals 1, back to the top of the stack, right? Boom. So this is to start off with a simple example. You can see we ran through this whole script, and when we get all the way to the bottom of it, the only value remaining in the stack is true. That means that this is a valid script, right? We successfully executed this script. If something had gone wrong, we might have just stopped execution during the script. If there was like an equal verify or something inside this script somewhere, it might have just stopped, said, no, we're done here, this isn't any good. Or we might have gotten all the way to the bottom and had false at the bottom, in which case, that did not execute successfully. So if we just stop execution, or if we get to false all the way down at the bottom, then we failed at unlocking our locking script, right? But this is a simple example, right? We don't have locking and unlocking. We just have this very simple math. So let's see if we have any questions before we move on to actually trying it out with some simple math. We'll try the simple math before we move to sort of a more realistic unlocking script.
Sure. We got one down here. They say this may be a bit off topic. We might have discussed this perhaps in a previous video, which of course you can check down below, but we'll see. You tell us. It's the question is about why a signature is necessary. Like if the public key is enough to prove the transaction is sent by a certain person, and then the follow-up question is there any way for someone else to send a transaction with their public key?
Okay, so
my public key, I guess, if I'm
right. So a public key is not enough to validate that the transaction came from a certain person. So let's walk back to this image here, right? And this locking script sort of locks this transaction to this particular pub key, right? Here it's the hash of the pub key, but it's this pub key, right? And the idea being, as this is locked to this sort of address, which is created from a pub key, so that only the person or the entity that has that corresponding private key can create an unlocking script. So when I lock this bit of Bitcoin that's in this transaction, so I've got one whole Bitcoin in this transaction, right? And I lock it to the hash of this pub key, right, which is formatted specific address. This is Mike's pub key, and we would presume and hope that then only Mike has access to the corresponding private key. So that means that once this Bitcoin, that one Bitcoin is locked to this address with this locking script, right? That's then Mike's Bitcoin. And if he wants to send it in the future, well, he has to present this unlocking script, which includes his pub key, but also his signature. And I think it was it unit 3? I can't remember which one, where we walked through signatures and verifying signatures. So we know that with the current state of cryptography, right, that only Mike, who is the only person that has access to that private key, can create this signature, can create a valid signature here, right, on this data. And so that way we can lock funds to a pub key, but only a person with the corresponding private key is capable of creating a valid unlocking script. So that's how that works. And if there's any, if the picture in your head of signatures and valid signatures is a little fuzzy, then I'd recommend going back to the unit where we covered that one. I hope that answers the question. Mike, do you have any more?
I'm not seeing any more right now, but I will let you know if they show up.
Okay, awesome, cool. All right, so now we're going to try it. We're going to go to this website and we'll try some very simple math. So we'll walk through the exact example that we just went through just so we can visualize it, which is fun. And then we'll do something slightly more complex. So I'm going to exit screen. Oops, I hit the wrong button. Sorry, Mike. Let me go back to sharing screen. Okay, sorry, I hit the wrong button. Tell me when we're ready to proceed, Mike. Okay, excellent. All right, just keeping Mike on his toes today. That's what we're doing. Hope you had your coffee. All right, so we are going to take this very simple script here, and we are going to drop it into this script simulator. So again, it's going to go 2, 3. Here it shows up as op add, and we use op equal, right? Again, in the examples from Mastering Bitcoin, the op is dropped because it's redundant, and that's fair. Either way is sort of a valid way to note it, but when you're actually writing the scripts, right, I think you do need to include op. Okay, so we have our animation speed. We're going to turn it super low so we can watch as this happens, and let's run it. Okay, we add 2 to the stack. We add 3 to the stack. We take both of those parameters off because we're adding them, and then we return the result, which is 5. Then we add 5 to the stack. Then we take those 2 off and check if they were equal and return true or false back to the stack. And we return 1, which is true. Yay, we successfully ran this script. And you'll note again, all those values start with 0x, right? That's like hex notation, right? Okay, cool. So now we did that. Now we're going to look at this, and I'm going to copy this value, but y'all want to take a second to look at this. 2, 7, op add, 3, op sub, 1, op add, 7, op equal. Any idea what that's doing? Right? You kind of got to read it a little bit backwards. But let's take a second to just visualize what might be happening there. Okay, 2 and 7 add, but then 3 subtract, 1 add, 7 is equal, right? It's kind of a difficult thing for a human to read, right? It's made for computers, not for humans. But let's take that, and again, let's turn our execution speed. Oh, I won't stop sharing anymore. Okay. All right. So let's take this, again, execution speed pretty low here, and let's run through it and see what happens. Okay, we add 2 to the stack. We add 7 to the stack. Oh, we're doing op add, so we take off those top 2 items and we add a result back to the stack. What do we get? What's the result? 9. Okay. But then we also add 3 to the stack, but then we're doing op sub, so we subtract, I think, 3 from 9, return the result to the stack, which is 6. Then we add a 1 to the stack, and we pop off 2 items for op add, and add the 7 and the 1, or the 6 and the 1 together. We get the result 7. Then we add 7 to the stack. Then we pop those 2 off for op equal and see if they are equal to each other. And ta-da, they are equal to each other. Okay, so that was a very, very confusing way to do a very simple bit of arithmetic. But I hope that kind of walking through this, helps you visualize, you just got to get used to it, right? If you're going to be working with this stuff, right, you just got to get used to reading it and how this stacking goes. All right, so we're going to
We had a question real quick, Hannah.
Yep, let's do it.
Are negative numbers supported?
Ooh, good question. I want to go with no, but I would have to double check that. Right, I haven't ran across that scenario. So I would have to go consult this here somewhere to double check on that one for you. Nice question. Okay, cool. Any others, Mike?
Nothing right now, but I'll let you know.
Okay, cool. All right, we only got about 10 more minutes left, so let's just get through this last example, right? Finally, we've led up to this. This is, again, is our pay2 pub key hash locking and unlocking script, and we want to see how they get run sort of together. All right, let's walk through it. All right, so first you can see, like, let's look back here. We have signature, pub key, op dupe, op hash 160, pub key hash, op equal verify, op check sig, right? That's what we got. And if we look here, we just line them up. So we start on this side first with the unlocking script, then walk through the locking script. All right, so it's kind of, this is confusing, right? So let's start with this first thing. The execution pointer starts with signature, puts signature on the stack, right? Then the execution pointer moves to the pub key. So moving to the right with each step, the value pub key is pushed onto the top of the stack on top of signature. All right, then we get to this op dupe. The op dupe operator duplicates the top item in the stack, and the resulting value is pushed to the top of the stack. So we have pub key, because it took, right, it pops off this first one, which was this pub key item, duplicates it, pushes that on. Now we have signature, pub key, pub key. All right, now we move along further. So the execution pointer moves to this op hash 160. The hash 160 operator hashes the top item in the stack with ripe MD 160 SHA 256 pub key, right? So the pub key first gets run through SHA 256, then ripe MD 160. The resulting value, pub key hash, is pushed back to the top of the stack, right? So it took one of those pub keys off, hashed it in all these ways, pushed this back on. Stay with me here. We're getting to the end. All right. Now we move to this where it was the pub key hash, right? That was in the locking script, right? So we're now right in the middle of the locking script, right? And it says the value pub key hash from the script is pushed on the top value of, on top of the value pub key hash calculated previously from the hash 160 of the pub key, right? So once we went to this operation, we had a pub key hash there. Now we're going to take this pub key hash value, put it onto the top of the stack. Now we get to the op equal verify. All right, this operator compares the pub key hash, encumbering the transaction with the pub key hash calculated from the user's pub key. If they match, both are removed and execution continues, right? So if they match, hey, we're good to go. If they don't match, I think in this particular script, like, we would just stop. Good. No point in continuing. This is no good. All right. Now we've checked that both of those match. Now all we have is a public key and a signature. And so we get to this next really important part. All of it's very, very important. But here's, the finale is we do op check sig. The check sig operator checks that the signature, right, this very important signature here, which is cryptographically created with the private key corresponding to this public key, checks that signature matches the pub key and pushes the true on top of the stack if true. Okay, now you might have spotted something here, right? If you're really following along keenly, if you already have some familiarity with this, in order to check a signature, we need the data that is being signed, right? The transaction, we need a pub key and we need a signature. So here, the data that is being signed is this full transaction, right? And we're not explicitly stating that, that sort of implies. So that's something to keep in mind there. And so if we then go and take the data from the transaction, check that is signature, take the data from the transaction and the pub key, and then check that data against the signature to check that it's all valid and it comes back as valid, then we have successfully unlocked this UTXO, unlocked that 1 Bitcoin locked here, and we can send it on to wherever Mike was trying to send his transaction, right? And if we look at this, we can see that this all the way after we do all this other stuff, we get down to the original values checked here. And because we had already duplicated this, right, and then used it in other parts of the transaction, we know that this pub key provided here is the same pub key used, hashed and used here, etc. So once we get through this, and you can come back here and walk through it slowly and think through various sort of stuff to just satisfy yourself that this is indeed a very good way to check that this pub key and signature matches appropriately with that locking script. So that's a lot. Let's go through and check it out, right? Here I have written this in a number of different ways, right? Because it's difficult for a human to read. But here we're looking at the situation where Bob, right, is trying to spend this transaction. So sorry, Mike, here we've replaced you with Bob. So this is, we have what
Very
this
hurt.
whole, I know, sorry. Here we have Bob's unlocking script, which is just his signature and his pub key. Then here is the locking script. And I tried to put some of this in bold to kind of make it a little, and space it out a bit to make it a little bit easier to read. These opcodes are sort of in bold. We have op dupe, op hash 160. Here's hash, right? This is some data. Op equal verify, op check sig. We can also read it like this. Sometimes you'll see it written out a bit like this. Op sig, Bob sig, Bob pub key, op dupe, op hash, blah, blah, blah. Right? So just sort of giving the idea that sometimes you'll see it notated like that. Okay, so let's go and try it. We only got 5 minutes left, but we can get through this. All right, a couple things to note here. Playing with scripts can get pretty complex. You need to get comfortable with hex and be very careful to get your formatting correct, etc. So let's simplify things a little bit here by removing the complexity of checking the signature, because it can be, if you want to try and use this scripting simulator, like you can give yourself quite a headache trying to get formatting just right while you do that. So for simplicity, for this example, we're going to remove the headache of formatting the signature exactly correctly. So we'll remove Bob sig and the op check sig, and we'll give you the values to run. So I've sort of simplified it so we don't have to mess with that headache today. All right. So we have Bob pub key, op dupe, op hash, op equal verify. So we're sort of skipping checking the signature, which you would never do in a real Bitcoin transaction, right? But obviously here, just to get familiar with how this process works, that's okay. We're going to do that. All right. How do I, hold on just a second. Where did I had all these values to run, did I not? Hold on just a sec. I've hit a slight snag. Mike, can I stop share for just like 1 minute while I go find some data?
Sure, no problem. You're good.
Okay, give me just a moment while I just go dig up the fancy data I had prepped for this. Let's see. Haha, here we go. And I'm back. Let's copy this. Okay, and where are we with the Zoom? I will resume my share. Oops, I want to be on this tab. There we are. Hold on. Okay, cool. All right, let's continue. Hold on, I gotta wait for that.
All right, we're good.
Here? Okay, cool. All right, so I'm going to paste this information in, right? Again, formatted slightly differently. Instead of going the long ways, we have lots of data, so I'm stacking it, right? Read it top to bottom, just to simplify for us humans, right? So Bob pub key, op dupe, op hash, pub key equal verify. Let's see how we go with this. All right. So we take that pub key, then we hold on. I fell behind on this. I'm going to run it again so I can help you walk through it. What are we doing? Okay, so we're going to run it again. Okay. All right, so we have pub key. We duplicate that. So we add another one to it. All right, then we do op hash and we hash it. There we go. Then we take that other hash that we had and we pop that off and check that it is verified. Boom. And we get 1 back on the script and as returned. And so this script executed successfully, right? All right, so we're a bit low on time. We got 2 minutes. So you all can come back to this website here too. It's in the exercise for the course, so you can play around with this. Again, be careful with the signatures. Formatting it correctly can be a headache, but it's really fun to play around with different opcodes, turn this animation speed right down low, have some fun with it, or you can just run through things really fast if you want to give yourself a headache and try and follow along with that. There we go. Okay. So I'm going to run through a couple more things on here really quickly before we do questions, right? A couple things I just want to note. What we covered here is, scripting, but actually a fairly simplistic script, right? There's pay to pub key hash, right? But pay to script hash is something that gets covered in Unit 7 of the course and is really important. And it is a way to do much more complicated scripts where you're locking funds to the hash of a much bigger script, right, then you might want to just add directly to the locking script. So then you can do all kinds of multisig stuff, which is really interesting, which is M of N. So you can say, hey, I want to lock these funds to the script. And what validates, what unlocks the script is to have a signature from N of N different keys, right? So I could say that's 2 signatures from a potential of 3 different keys, or 3 signatures from a potential of 5 different keys, etc. This is really important because multisig is used in so many different applications in Bitcoin. It's really cool stuff. We could do an entire session just on multisig, but something to be aware of there. Quite cool. The book dives into that. All right, looks like an address that starts with 3. It might look like this. So that's a pay to script hash address. Yeah, and as I said, get so many more options with that. Some drawbacks. A wallet needs to remember the script that was used to create the hash. We won't dive into that, but there's benefits and drawbacks as there are with everything in life, right? Here's what multi-sig kind of looks like. This way I picture it in my head is you're sort of locking funds, and sometimes people use it a bit like an escrow service, right? We're going to lock funds here, and 2 of these signatures, 2 of 3 different signatures have to agree to move the funds, etc. You can have like 2 different parties and some sort of arbitrator or mediator or something of that sort. You can do really cool, interesting things. Okay. 2 things that are not directly covered in the course, because they're much newer things to Bitcoin that I just want you to know exist, is SegWit. And SegWit is segregated witness. It's basically just a different way to store, transaction data and signatures for it, stored it kind of separately in the blockchain data, right? And signature is definitely still there, right? But it's just stored slightly separately. There's so much history behind this and why this happened. Again, we could do an entire session on that. It fixed this problem called transaction malleability, and which allowed for the creation of the Lightning Network. So it's and it was also important in sort of the scaling wars when there's all kinds of disagreements about how to scale this technology. So really, really impactful bit of change to Bitcoin. Very interesting to dig into that at the moment. Just be aware that that's a thing. And then just last year, we had the activation of some functionality called Taproot, which provides for the option to do scripting a bit differently, and it also allows to make it more complex, right? Which is more options, but also more complexity for wallets, etc. So that was quite a lot. Mike, do we have any questions?
Okay, well, I'm taking a look at the chat right now. I'm not currently seeing any questions, so I'll do a thing where I vamp for a little bit and remind everyone that we'll be back here next week to go over Unit 8. And of course, if you haven't seen any of the other videos of these series, you should go back and watch those. And they are, of course, a supplement to Saylor Academy's Bitcoin for Developers course, which you should take also, because this is a supplement to that. I, of course, want to thank everyone for joining us, and of course, join everyone in the chat and thanking you, Hannah, for taking us through yet another unit here. But I'm not seeing anything coming through the chat right now. So if any question comes up, you think of a question later, you can put it down in the comments, or save it to next week. Maybe ask it at the start of next week's episode unit. Oh, here we go. We got a question coming in right here. There we go. The vamp just long enough. What is the maximum script size?
Oh, great question. I can't remember it off the top of my head. So there absolutely are limits. There's limits to the amount of outputs you can have on a transaction, 483. There is some limits to that. I'm not going to pull it off the top of my head right now, lo siento. So I'd have to, maybe I can drop it in the comments. I'll go find that data for you and drop it in the comments on the video. Yeah.
All right. Well, there you go. We'll find it for you. But thank you very much. Thanks for the questions. Thanks for the thank yous in the chat. And again, thank you, Hannah. But so we'll see everyone same time, unless other countries change their times. Also, who knows? We'll see you a time next week, everyone.
By next week, I will have gotten used to the time zone shift, so we should be good. And next week is the last one, right? Last unit 8.
Right.
Yeah.
All right. Sounds great. Thank you, everyone. Thanks for joining us.